Okay, so I planned on having this video out before 2017 started, but I'm lazy. So this is going to be part one on my new channel for the esters series of videos that I'm going to be doing. This channel will also deal in other things like electronics and general science experiments. But I really want to get started with esters, and I'm going to do a classical demonstration of one today. But first, let's talk about an ester. So, there are a specific class of organic compounds that have generally fruity characteristics, but fruity smells, rather, as part of their main characteristic, but not always. They can also have unpleasant odors. But because they're relatively volatile, every ester has a general unique smell, and they're used in things like the perfume industry for food flavorings and stuff like that. Now, the way we make esters is by reacting a carboxylic acid with an alcohol of some kind. In this case, for the carboxylic acids, we'll essentially get rid of the hydroxyl group over here, replacing a hydrogen with an alcohol group. And the reaction normally does not proceed at a reasonable rate. It takes forever. So we have to add catalysts to basically speed up the reaction. Also, because it's an equilibrium reaction, we'll have water as a side product, so you generally need something to sequester the water, like sulfuric acid, for example. But today, I'm going to be talking about something called methyl cinnamate. My handwriting is amazing. And without going into details about the naming conventions of methyl cinnamate, first, if you have not seen these two videos that I'm going to put a link for in the description, one of them is the Nile Red video, the other one is the Doug's Lab video. I highly recommend you check them out, mostly because they cover in-depth mechanisms that I don't for the reactions, and they're generally better production and value and quality than I am. This is really just me dicking around. But in order to make methyl cinnamate, what we have to do is react a carboxylic acid, in this case acetyl salicylic acid, which is a mouthful, also known as ASA. We'll convert this to salicylic acid, and then we'll react this with methanol to grab our methyl cinnamate ester. Now, there is a very convenient source of acetyl salicylic acid. If I can move this without destroying my camera setup. I'll just pretend that didn't happen. In the form of aspirin pills. There's a bunch of videos that already cover the history for aspirin pills, specifically how they came about, the varied uses, etc. Everybody's familiar with it. Now, the conversion from acetyl salicylic acid to salicylic acid is not the first step in most synthesis videos for this particular ester. What you do first, for most of them anyway, is we have to actually perform a recrystallization of the aspirin pills to get rid of all of the gunk, the binders, and stuff inside of it. Now, I actually tried doing this on 2 occasions using the same source of aspirin, in this case from a public supermarket. And both times, for whatever reason, the crystals, after recrystallizing from acetone, got superglued and stuck onto the glass. That should not happen. So I looked at the ingredients label, and I noticed one of the inactive ingredients was something called triacetin or triacetin, and basically this is the equivalent of 3 glycerin molecules stuck together. So it's effectively acting as a sugar, and my best guess is that because of the triacetin, it's also extremely soluble. So along with the ASA crystals, it's also getting stuck in solution, and it's basically making them stick to the glass. I did try recrystallizing it again, And unfortunately, I sort of wound up with this messy, freaking toxic sludge gunk. So, what I'm going to do instead is, I'm hoping this will work, I'm not going to perform a recrystallization. I'm going to be using relatively impure ASA. In other words, I'm just going to be taking the aspirin pills, grinding them up, and then using that in the reaction, and hoping that the triacetin and all of the other gunk doesn't interfere with the reaction. If you do this reaction, the aspirin pills that you choose should have the least amount of binders available in them. If it has triacetin or triacetin in them, I would not recommend buying it. I would not recommend using it for the synthesis. But if anybody else has actually done this before and they've run into the same problem, let me know, because I'm interested if my guess is correct in this. Anyway, so after the recrystallization of ASA, we're going to do a conversion to salicylic acid. We have to get rid of the acetyl group, and in order to do this, there's two main methods. We can do a base hydrolysis or an acid catalyzed hydrolysis. And in my case, I'm going to be using a very simple acid catalyzed hydrolysis. The procedure I got off the Science Madness forums. I'll also put a link to that in the description. And it's relatively simple. Supposedly the yield is about 95%. So basically we're just going to add water and acid, in this case hydrochloric acid, to get rid of the acetyl group, and run it under reflux for, like an hour and a half or something. So I'm actually going to set that up right now. I'll go over the exact I'll go over the exact procedure, and then I'll have everything set up in the next section of this video. Alright. And stop. Okay, so I got a little bit excited. I forgot to mention some stuff about the general formulas for carboxylic acids and esters, but in general they can be identified because you'll have an oxygen double bonded to the first carbon in the chain, and then the naming conventions depend on the number of carbons following that bond. Usually it's an alcohol for the esters. There's a bunch of YouTube videos that you guys can check out to learn more about the specifics regarding that. But today is synthesis day. So, as I had said before, what we're going to be doing is we're going to be crushing up these aspirin pills, binders and all. We're going to be reacting them in a reflux setup with water, and in this case our catalyst is going to be hydrochloric acid. Now, as a warning, we're going to be working with strong acids and bases. We're going to be working with strong acids, hydrochloric and sulfuric later on, so in order to mitigate the risks involved, I actually am going to set up a simple base bath just to neutralize any potential acid spills, and this can be easily done adding an arbitrary amount of baking soda to some water that I have here. Yeah. And I can add more later if I need to. Personal protective equipment, of course, is going to be gloves, nitrile in this case, goggles. Just as a warning, the acid concentration that I'm going to be using for the sulfuric is 98%, and it's really good at sequestering water. It's really reactive. So there's really not much that can stand sulfuric acid at that concentration, even nitrile gloves. It's probably going to eat through them given enough time. As has been evidenced before when I felt some acid stings that I didn't notice, because the sulfuric had actually penetrated through the rubber and started attacking my skin. So really, the gloves are just a precautionary measure. If you notice any acid spills on you, you want to take your gloves off right away and start washing your hands. And those are my last gloves, whatever. So, I'm going to... what am I going to do? Oh yes, one more warning. Hydrochloric acid fumes a lot, and despite the fact that this bottle is actually closed and sealed tight with a cap, after I took it out of its plastic packaging and opened it, right now the fumes are stinging my eyes. They're actually escaping from the container, and they're quite corrosive. So, if there are any chem students or graduates or whatever that is watching this video, you usually want to work in a fume hood or outside when dealing with these things. Otherwise, just a friendly warning. In an enclosed space like I'm working in right now, hydrochloric will generally kind of make your eyes water. There's really no getting around it, unless you have like a fan blowing or something. Okay, so I'm going to crush these up and then begin, Okay, so according to my math, my lovely math, we need 69.2 tablets. Well, I don't really feel like measuring out 69.2, so I'm just going to average and say 75 tablets will be dissolved in... Okay, I'm bad at math. I have to do this really quick. But let me come back to the video as soon as I redo this. Okay, so I figured it out. I'm bad at math, but I can essentially, we can essentially do it this way. I was not able to fully break up all of the aspirin tablets because the bag that I had used broke, unfortunately. So I have some unbroken up tablets in here, but hopefully there's enough surface area for the reaction to get going. I don't foresee a problem with that. So the work up here is essentially an acid-catalyzed hydrolysis of acetylsalicylic acid to salicylic acid. What we're going to be doing is we're going to be reacting the equivalent of 70 tablets of aspirin with 300 milliliters of water and 5 milliliters of hydrochloric acid, which will act as our catalyst. This will get rid of the acetyl group, and we'll be left with the salicylic acid, which can crystallize out, and hopefully, I'm hoping that'll drive away the impurities, because there's kind of a lot in this particular instance. Normally I wouldn't use such impure tablets, but they were cheap, and I'm too lazy to go shopping at Walmart. So, we're going to reflux this on max heat for about 30 minutes. I'm going to set up a condenser after I do this workup, and then I'm going to crank the heat up for about half hour. But let me go ahead and put on my gear. Alright. So this workup, as I said, calls for 300 milliliters of water, distilled, not purified. Just 3 additions of this full grad cylinder. Normally you should not fill a flask above the halfway point, especially if you're going to be doing distillation or reflux, because the materials inside can jump straight into the condenser. But I'm not too worried in this case, since all I essentially have is water and a weak acid solution. But in general, since this is a 500 milliliter round bottom flask, I would not put more than 250 milliliters at a time. Material. That's too much. That's too much. There we go. As I said before, this calls for 5 milliliters of hydrochloric acid, which will act as our catalyst. Otherwise, it would take forever, like weeks or months, for the reaction to progress at any reasonable rate, even under heat. This way, 5 milliliters might not seem like a lot. but it's sufficient. That's more than 5. Luckily, that's why we have our base bath. I'm going to cap the hydrochloric acid since I don't need it anymore for this reaction, and I'm going to put it back in this plastic container that it came shipped in, just to prevent the fumes from escaping and corroding everything around it. If I was psychotic, I would put this in like a refrigerator or something, but it's not that important. We only need 5. That'll work. The dissolution of hydrochloric acid in water is not particularly exothermic, since it's mostly water anyway, so I can safely dump this in the base bath. There's just going to be a lot of bubbling. Which, since this is sodium bicarb and this is hydrochloric, should give us salt and CO2 gas. Salt in this case is sodium chloride. Okay, so we have our overly full mixture, which I'm not too comfortable with, but I'm going to set this up for reflux. I'll come back as soon as that is set up. There we go. Okay, so let's talk about this obviously super safe and not at all dangerous looking setup. It is. I'm just too cheap to buy ring stands. That's basically why I'm science bum. Anyway, so this is what's known as a reflux apparatus, and essentially what we're going to be doing is we're going to be boiling liquid inside this flask. And as it boils, we have a water pump hooked up to a condenser column over here, also known as a Liebig condenser. And as the water boils, the solvent that we're using in this case is going to go up the condenser column and cool down and fall back, meaning we get the same reaction going without any loss of solvent, theoretically. So I'm going to go ahead and plug this in. Crank up the heat. I'll put it on medium first and then we'll go over to high because this is a cooking channel, right? And I'm basically going to keep an eye on this for the next half an hour. So, in case it wasn't obvious before, I was kidding when I said that this was not dangerous. This is an incredibly dangerous setup that I have right here. And the only reason I'm doing it this way is because the ring stands and the clamps to hold these flasks in place are ridiculously expensive, especially the 3-pronged ones, which are the ones that I really like. And I don't really feel like spending $30, $40 on lab equipment that I'm not going to be using very often, so also I'm cheap. Oh, and in order to insulate the heat, since we don't get very good surface contact with the hot plate, now I'm just going to put on up aluminum foil. That looks totally okay. Yeah, that's safe. Alright, so I'll come back after half hour once this is done refluxing, and after letting everything cool, we should be getting salicylic acid crystals forming, which look like white fluffy powder. So we'll know right away whether or not this has succeeded or failed. Alright, see you soon. Okay, so this is the part where I start screaming and cursing, more like crying and weeping. There was a profuse amount of smoke coming from my hot plate, and I forgot that the pan that I was using had some melted gunk on it from this yellow foam that I had accidentally forgot to scrape off before putting on here. I've been at this for like 10 minutes and it's not coming off now, nor is it coming off on the hot plate. I am not happy right now. I'm very sad. So, I guess the next video of this is going to be part 2, where I just go straight to the salicylic acid crystals. Yeah. This is my fault, as is every other bad thing that's ever happened to me in my life. Anyway, stay tuned for the next episode. Yeah. Depression.